everyone. Let's start. In response to your questions about the survey, the survey is anonymous. So I don't see who has said what, where, which is great. That's how it's supposed to be. But because it's anonymous, I cannot put on eCampus. At least I have not been able to find the way to give credit or points for those who do the survey. So I can see who did it, but I cannot give you points for some reason. So, I mean, I can see that you have finished it, not what you did, obviously, but those who have finished it, I will give you 30 points on TapHat, because that's how I can enter it. And, you know, that's what I plan to do. You have not seen it because I have given up until Monday, I believe, or something like that.
Is the service still available?
What is it?
Is the service still available?
Service, what service? Oh,
survey.
The survey. The survey, yeah, it is it not? Have you tried it to use it and it's not available?
It's still there.
It's still there, yes.
Where is it and what is it about?
It does not, look at it. And then you will see what is wrong. It's just want to receive your feedback about how to.
Where is it?
Okay. Can I talk to you about during that in office hours? If or others, please help me. Help your colleague to find it.
It's on eCampus. It's
Yes.
about
Okay.
teaching.
Yeah, it's about teaching, and I have to tell you why I decided to do the survey. I always have a sense, and it's like a sense that I get about how the class is going. I am not having a good feeling right now, and so, and I don't, you know, it's kind of all kinds of different things, but my feelings, maybe I don't see you in person, I don't know, maybe those that I see are students who have problems, I don't see others, but I don't get a sense of, I don't have a good sense that this class is going well. So I don't want to put words in your mouth, but I wanted to find out from you, where are the areas that need improvement and where I can help you more. My goal in this class is that everybody does well. You know, I told you that my goal is that everybody learns, and then giving grades is secondary. So because I have that just kind of feeling, and I want to see how things are going, I want to get a sense from your survey, and I would like your advice. And that's why I gave you also a section. Don't be brief. You don't think to spend a lot of time to tell me what are the things that will help you, and I will try to do the best I can. So that is why the survey is there. The other thing that I thought is to do, since people are not coming to the office hours, I decided that I will use 1 hour, not both hours. I will use one of them to just solve problems that will help you with the homework. I'm not going to necessarily do the homework. Today I decided I'm not going to solve the homework, but I will do some things using the homework to help you. And I may do it with other homeworks as well. I mean, I plan to do this with other homeworks as well, because I do understand that what is happening as we go through this class. We have to use many concepts that we have seen and may not remember from before, that we see for the first time now, or we have seen and remember. We have to combine all of these, and that combination is not obvious. And I would like to help you get to do this, because that's the idea for this class, to bring a lot of pieces together, in addition to introducing some things that you may have not seen before, or you have not seen before. And then the idea is to put all of these things together, because trying to understand the design or try to attempt the design of a system, it's the highest level, all right, in engineering. Design is the goal, and design is the most difficult. Analysis is always easier because somebody else put things together, you just have to analyze it. But design, you have to make the choices. And it is difficult, I understand that. And I would like to help, because I would like you not to solve your problems, I would like you to learn how and help you to solve them. So that's the whole goal, if I may. So with that, I would like to continue and say the following. We have seen, and I will repeat, you will see me repeating topics multiple times. Because I believe instead of just going on a straight line and teach the topics one like after the other sequentially, we're not gonna do it like that. People don't learn languages like this. You start talking about what is the end goal. And even from the beginning, when this end goal may not necessarily be easy to understand, but then bring it back regularly. And every time we're gonna bring it back, not only you're gonna see it again, not only I will repeat things, we are gonna also add some new material to it. And I believe this is gonna help. That's my thinking. Otherwise, if I were to do the whole thing sequentially, we would wait until the last week to talk about receivers. And I don't think anybody's gonna gain from that, from this class. Okay, so last time I talked about, again, the homodyne receiver or the tuning radio receiver, as people called it, a very early version. We talked about why it was not a good design and why people moved from that to super heterodyne receivers. And then we talked about the super heterodyne, and then which where you do mixing through a local oscillator. And then we talked about the problem of the image frequency so for example, if you have a frequency which is somehow close to the LO at the same distance from the LO as your RF, from either below or above the LO, then in that case, you start having a spurious IF that is not it does not carry the information from your own signal. And it's very difficult to get rid of this IF because your IF filters will not be able to exclude it. So then how did people manage that? They managed it by creating the image reject heterodyne, super heterodyne receiver, where you split the signal right after the first mixing into two paths. And then you mix each path separately again, or you do it before the mixing. You split the two paths. There are two separate types of super heterodyne. You split the two paths before the mixing. You mix the signals out of 90 degrees out of phase. So one path, you call it in phase. The other path, call it quadrature, because it's 90 degrees out. You mix them, and then you either recombine them or you mix them again and so forth. But the idea is whether you have a mixer before, a mixer after, two mixers after, and so forth. The idea is to split eventually your signal into two paths and introduce a 90-degree angle into one path in the phase. And this way, mathematically and accurately, you cancel out the spurious, a very large number of spurious frequencies that would be very difficult to get rid of them in the IF. That's the basic idea. And then we talked about the direct conversion receiver and some of the issues with a DC offset and so forth. And there is a possibility of getting DC through your receiver and everything. And how people have dealt with that by also introducing I and Q paths in a direct conversion receiver. Okay, so that is the basic idea. Now, what I would like to do is to talk about receiver specifications. If you try to do a design of a receiver, then you will have specific numbers in mind that you have to satisfy. And of course, one, as you can see here, is the frequency of operation. So if I were to write here, I would say number one, okay, well, that does not wanna, I don't know what the problem is. One. All right, well, here, let me try again. All right, I will just talk about this and I will show here. One is the frequency of operation, and the frequency, as you can see here, of operation here is important to have, because that's exactly where your receiver operates. And I told, and then you will have selected this by Monday, of course, your frequency of operation, your bandwidth, and the type of your receiver, hopefully. Then these are fundamental. After that, you talk about dynamic range. What is the dynamic range? And you can see it here in the picture. The dynamic range, practically, I think it's, the problem is my pencil that has probably, no, my pencil is supposed to work. Okay. All right, then cut. There it is. I mean, I'm sorry, there is nice software to work, but it also has its own problem. So the dynamic range says the following. In a receiver, we bring a voltage in, all right? This is the voltage here that you bring into a receiver, the voltage. So when you bring the voltage in, you would like to have a receiver that can go from very low voltages to very high, and that is called dynamic range, because then you can go from very, very low signals to very, very high signals. Unfortunately, this dynamic range has its own problems, all right? So you see a reverse relationship. Unfortunately, what happens in most designs is that the two parameters we want to increase at the present time are related through a reverse relationship. So that's why we always have to do a design compromise. We always have to do what we call the trade-offs. If both things were increasing at the same time, and if both things were decreasing at the same time, then it would have been much easier to make a good design. But so for example, here we would like designs to have very large bandwidth, but what is the problem here is that the dynamic range becomes narrow. See here. And there are reasons for that. So of course, in the design, we have to reduce the noise floor. The higher the noise floor, the more your resistive losses, the more your dielectric losses, the more whatever other sources of noise you may have from your transistors and so forth. We talked about some fundamental, the thermal noise, which is fundamental to resistors, and other resistive losses you may have in the dielectric. And then you have some flicker noise, which is important for the lower frequencies, and some other things that you come from the transistors. So all of these are noise sources. As your noise grows higher, then your bandwidth grows higher, then you have a reduced dynamic range. What happens when the noise goes higher? So you cannot see as low signals anymore. You lose your signal into your noise. For example, if here your signal were to be at that level, and you can see the signal in the low bandwidth, then as you go into higher bandwidths, then the signal is lost into your noise and very difficult to demodulate it. The other thing is, of course, as the bandwidth increases, then your breakdown voltage increases. And also as your frequency increases, or the speed of the device that you have increases, your breakdown voltage increases. And then for those of you who have done MOSFETs, and remember that is usually the current flows from the gate. So the gate looks like this. If we talked about that in some time. The gate looks like this, and then you have your drain here. And then the gate length and the gate and the material below the gate, the gate length itself and the gate, the gap, are extremely important in how much current will go from the gate to the drain and how much current you're going to have from the transistor. However, what happens is, to be able that, you need to do two things. You need to reduce the gap below the gate to make it faster, to make the electrons faster to go through. And then also you need to increase the length. to be able to have a better performance and more bandwidth. In the process of doing that, however, because you reduce the thickness of a dielectric, the breakdown voltage becomes very much lower, because now you put a lot of voltage into a smaller thickness of a dielectric, and then so you have a breakdown. So you see, and the same thing applies with the bandwidth. So for example, as you increase your bandwidth, not only your noise goes higher, your breakdown goes lower, and then you lose your dynamic range. So dynamic range is very important. Then we talked about the FT, which is exactly where your gain of your amplifier becomes 1. And then the FT and the F max are extremely important, because both frequencies show you they're very high frequencies, obviously. So if you operate a transistor at 40 gigahertz, your FT and F max have to be very high, like 250, to be able to have good performance. Otherwise, if you're too close to your FT, that means that your the gain practically of your transistor has no gain. All right, so that's what it means, not a good transistor. And when FT is very high, if max is very high, then you have substantial also issues with the intrinsic and then external performances of the device. The intrinsic performance is important for FT. The external also parasitics, in addition to the intrinsic, is important for the F max. So both of them have to be very high. And noise figure also extremely important. Noise figure, we will see this again. So I'm not going to spend too much time on noise figure right now, but because we are going to calculate that later. Noise figure, however, is extremely important because it's connected to your losses. And we said you have 2 types of losses, like more than 2, but practically you're going to have losses from your device, and then you're going to have losses from your matching networks. And matching is going to be absolutely critical to make a device operate like a low noise amplifier, or if you are in a transmitter, like a high power, high gain amplifier. All right, usually low noise have lower gain. Let's assume you want a high gain amplifier, you can compromise your noise. You still have to match it. And then what you're using in your matching networks are extremely important. Now, your device is going to be whatever you have intrinsically in your device, plus the parasitics, external parasitics. Say, for example, what are the external parasitics? Your device comes with your pads. All right, so something else can connect to it. Those include parasitics. And your designer, your device designer, not you, you're going to get your device from somebody for, say, for most receiver designs, they will give you the performance in specs. So they will give you the noise characteristics of this device here, or what we call the signal to noise ratio, or so they can give you either just noise characteristics or SNR, signal to noise ratio, or it can give you this factor, which is called the noise factor. And all are connected to 2 losses, like resistive losses due to metals, resistive losses from metals, can be resistive losses from dielectrics, and then can be resistive noise from the device. So plus intrinsic noise from device. All right, so all of these will be incorporated here. And then as a designer of the receiver, your goal or your work will be to identify the matching networks and then identify the same thing here, your F of this network. So eventually you would like to find the F of the whole device. So practically, how do we define the noise factor? F is the signal to noise ratio that goes in divided by the signal to noise ratio that goes out of your device or your whatever circuit you are analyzing at that point. All right, so it could be a 2-port network. And if this is SNR I that goes in, and this is SNR out that goes out of the system, then the ratio of the two is the noise factor. That noise factor, the way we have defined it, at best is going to be 1, is the optimum, which practically says that in terms of noise, your 2-port network does not add any noise to the system. All right, so optimum F equals 1. Then we have the noise figure that many of you have heard, which is like the 10 logarithm of F. And then why is it 10 logarithm? Because F is always in terms of power, all right? When it comes to noise, yes, we are using equivalent noise sources like voltage sources or current sources, as you have seen in active devices. But here, when we start talking about networks, we are talking about power, noise in power. We'll come back to noise, temperature, and all of this. I would like to show you that now because we have talked about networks. And I would like to show you how eventually we will calculate the losses of a network. Practically, as you remember, we combined networks, and we said that if we have networks that are connected like that, then if we identify that A, B, C, D matrices of 1, 2, or 3, then practically we can combine them to find the total one. The noise figure is not any different than this or independent. Practically by using this kind of approach that the total A, B, C, D is going to be the product of the 3, then you can also demonstrate this very important here formula, that your F noise, the total F noise, if this is number 1, if this one is number 1 and has a gain, we call the gain of that G sub A1, and then this is number 2, G sub A2, and so forth, number N, G sub AN, then practically your total F is given by this summation, F1 plus this formula, and so forth. Now, why is that important? Because you can take your receiver, and let's assume that you have just a simple receiver, your antenna. You have here your bandpass filter. You have here a low noise amplifier. And let's assume you do one mixing for a moment. Hello. Then you have here your IF filter. This is your RF, and so on. Let's assume you stop there for a moment. Then you can split that into the antenna. We're not going to design antenna, so this is going to be your GA1, F1. And let's assume for a moment you can include the antenna, or you can assume that your input is here, okay, which we are going to do in this class. So input
I have a question.
is here. Yes.
Is that supposed to be F2 minus 1 over GA1?
Yes. Thank you.
I think that should be alpha, as it is on the notes.
Okay.
It's not A, it's alpha.
Okay. Alpha. Here they have it A. It does not matter. Okay. So, and then F2 and so forth. Okay. So here, either you can start, you will see applications where your first network is F1, or they will say that this one here is my input. I don't care about the antenna. I will assume whatever comes from the antenna is my input here. And this one is my F1 and has, of course, a gay alpha 1. And this is my F2 and so forth. So practically, then you can treat each one of them as one 2-port. Even if this is a 3-port, eventually you can treat it as a 2-port, as you will see. And then by using this formula, you can find your noise factor of your whole receiver, at least the part of the receiver we are responsible for. All right, that's why this formula is important. So you can break down your whole receiver into parts. And that's what we are gonna do. Every part of your receiver that you're gonna design is gonna be 50 ohm line in, 50 ohm line out. And if there is a matching, it will have to be here, okay, inside your network to make it easier. That's what I would suggest. Others may select to do it a little easier and say, I don't wanna probably have one matching network from my filter on one end and another matching network from my low noise amplifier on the other. And I would like to just match them directly. You can do that too. But at the end of the day, the easiest thing is to break your receiver into parts and deal with each part separately. Identify all of the characteristics for each of these parts and then combine them. Okay, that's why this is important. Now, with that, since we are talking about noise, and I said noise is, we have seen noise before. We have not talked about it in the form of noise, but we have seen losses and we have talked about the impact of losses on Q. And do you remember why we talked about losses and then indirectly it is included into Q? Why is that? Do you remember how we have defined Q? How have we defined Q?
1 over the bandwidth.
Yes, that is the outcome. You remember that, all right? So Q in reality is 1 over the bandwidth. Very important relationship. If you know one, you know the other, obviously.
And it seems like that corresponds to the first graph, that as bandwidth increases, the noise floor increases as well.
Yes, exactly. You see that correlation here, all right? Absolutely, here. Absolutely. So here now, let's look into this. So it is a simple, it's just a correlation, I call it here, but we have seen this formula. How have we defined Q before we found the formula? We defined Q as what?
Is it sensitivity or, oh, I guess.
Yeah, you remember though, it was W, what? W, could you tell me, somebody?
The resonant frequency over W2 minus W1, or is it the other way around?
It was, Q was the ratio of two things.
The stored magnetic energy or electrical energy divided by the dissipated power.
Exactly, it was the stored magnetic and electric divided by P sub D. You remember that? That was the initial definition, the original definition. And then of course, there are all kinds of outcomes from this. Now,
and dissipated
yes.
power is power lost in the system.
Yes, yes. Okay. And this one now, the PD, is power loss in where? In resistors. And these are resistors you may have incorporated explicitly, all right, into your design. In metal losses, which are also resistive losses. And dielectric, all of these are thermal noise. All of these losses or all of these mechanisms that we call losses here give rise to what?
Dr. Katehi?
Yes.
What is the word
below metal.
Dielectric, sorry. Okay, all of these losses, what do they give rise to? Noise. What kind of noise is that? Thermal. Remember? We'll see that again. So your Q is another measure of your noise. And why do we call Q and bandwidth in the passives and noise figure in the actives? For obvious reasons, because obviously in passives, the only noise that you have is thermal noise. All right, only noise in passives that you have is thermal noise. But when you start having active devices, you have other types of losses, not just thermal. So those who dealt with thermal noise, in the beginning, we started calling those resistive losses, and then eventually Q, and eventually we went to bandwidth. But when you go now into bigger systems, instead of Q, you're talking more about sensitivity or noise, all right? But they all mean the same. Any questions so far? So that is in terms of concepts. But now I would like to go to the homework, all right? Because we'll come back to noise in more detail. Yes.
So is another way of thinking about it, Q only has linear losses and F has nonlinear losses?
How do you know, how do you define linearity?
Directly related by a coefficient, I suppose.
But what to what though?
Voltage to currents. Voltage to current.
That, yes, in that regard, yes.
Okay.
In relation now, when you go to power, however, all right, the relationship between power and voltage is not linear. I mean, it is linear, but eventually if you go only with voltage, all right,
V squared over R.
VI, it's squared.
Right.
So, but I understand what you're saying. Yes, between like a V and I, it is a linear relationship, all right? The relationship between V and I, it's linear. That is true for passives, practically. And because of that, we do superposition. You know, the interesting thing is that in noise, you cannot always superimpose. So we have to be careful when we do that. We'll talk about this a little later. But in passives, we will have to remember, yeah, the V and I is, but when you start going into V only, it's not linear. But if the noise is not correlated, you can sum it up. We'll go in details. I don't want to talk too much about this. I just want to remind you that, yes, remember, resistors, in all passives, the only noise we have is resistive losses or resistive noise or thermal noise, as people talk about it most of the time. When you go away from those, we have thermal and flicker noise and some kind of other types of noise depend on the active device. So it's not only that. But in any case, thermal noise, only passives, we talk about Q. Okay, and then we talk about bandwidth, and usually bandwidth and Q have that relationship, meaning that the higher your bandwidth, what happens, the lower your Q. Okay, but also Q is directly related to losses. So you're gonna see, of course, some other, we talk about, we will define Q also later in passives, especially in filters, in terms of what we call the insertion loss. Also loss, the same kind of loss. It's not a different loss, it's just a different way of talking about it. In any case, again, here, what did we learn? What do we remember? Passives only, resistive loss, either in resistors as lumped elements, in metals, or in dielectrics. That's thermal noise. Non-passive, meaning active and everything, we have multiple thermal, shut, and flicker noise, all right? But thermal noise most of the time is the one that takes over, all right, in our especially systems. In any case, that is so far. Any questions about these concepts as concepts? Okay.
I guess one more question relating to
Yes.
this and to the projects. So
yes,
the whole bandwidth issue, is that what makes 5G kind of more challenging, because 5G has greater bandwidth, and so you have to deal with the more sensitivity, the noise, and breakdown voltage?
So, so here it is, I think, what makes it 5G more challenging. Bandwidth is also connected. Of course, bandwidth and Q are connected. Higher bandwidth, lower Q is a problem, obviously, all right? More noise in place. However, so that is one trade-off. But bandwidth is important because you can transfer more data. You need more bandwidth to be able to push a lot of data in there, into the system. For example, when they say 1 gigabit per second, you need every second to push 1 gigabytes through the system. And you cannot do that without having enough bandwidth. So the challenge with 5G is that you need to have the maximum possible bandwidth that you can be allowed to use with the maximum possible sensitivity in your receiver. See, and that's a problem already because of that. You try to optimize two entities that are connected and in a reverse way. Because ideally, I would try to optimize my bandwidth and optimize my Q. And both have to be high, and I can't. So that's the problem of the design, all right? You have to find the sweet spot, as they say.
Is there an equation that relates data transfers to bandwidth?
Yes, and we are gonna look about this. Yeah. We are gonna talk about this. We will have time, practically. But there is, yes. Okay, can I go to our problem? Yes.
Sorry, just one more thing. So is more increased bandwidth allows more data transfer because basically you have more channels for the data to travel on?
True.
Okay.
Yes. You have more channels and therefore you can demodulate them independently. All right, and then the channels have to be separated by something. I mean, if you see, if there is, we have not covered that, don't have time in this class, but 5G is using OFDM. OFDM is a type of modulation where you use multiple channels. And some of you who have been looking probably for 5G receivers, you will see how many different channels they're using, sometimes up to many. I don't know, I don't want to cite like 18 and more. There are some extreme systems they have in the hundreds. Now, however, you have one compromise. These channels have to be orthogonal, which means that when one channel has a peak, like when you look at the frequency domain, all right? When one channel has a peak, then one other has to have a zero. So you cannot separate them by 1 hertz. See what I'm saying? You cannot you are limited in how many channels you can put within your bandwidth. And that's the problem, because the channels have to be orthogonal to be able to modulate them and demodulate them without errors. And that's what limits. So you're absolutely correct. Your number of channels tells you how many data you can put through. And because of that type of modulation method, which is very popular right now, you need a specific bandwidth. And that's why people want bandwidth. Bandwidth is gold right now in 5G receivers or transceivers. I mean, both transmit and receive. Any other questions? Okay, now remember Q, okay? Remember losses, remember noise. Now we are going to your homework. And I will start now and I will continue at 3 if we finish with this class. And I would like as many of you to join me also then. But let me look at the homework 5. homework. 4, I said 5, 4. 4. Okay, I'll take this one first, and then I'll go to homework 4 solutions, and not exactly that. 4, forgot, solutions on the right. Okay. I'm not solving you everything here. And if I do, that's okay. I will still like you to have a good solution in the problem. When you have, I'll say something generic right now, which you're gonna use in any other problem I give you and I ask for similar things, or in your project, okay? So let me add here one page so I can talk about this. When you have a passive circuit, see, that is not, anyway, when you have a passive circuit, so, and then it has a combination of resistors, capacitors, inductors. It could be, now this is whatever I do here, it's not real. I'm just doing something just to show you. Let's assume that you have something like that. And you wanna find your Q or your bandwidth, okay, or other things. Then you have to be systematic on how you look for things, all right? And in the problem that I gave you, I explained to you physically where the different elements in your equivalent circuit came from. So why am I saying that? Why am I saying that you have to be systematic? Systematic means I will start with everyone. Let's assume you have a capacitor here too, another capacitor. I will start with every type of circuit separately. I will look at capacitors first. I will look at inductors and resistors in groups. I'm not gonna lose myself into every, like into a cacophony of every single circuit component and then get lost into the weeds, all right? Because that's gonna happen. So that's how you're gonna have to be systematic in every design to be able to manage the complexity. So here, for example, in that circuit, and let me in fact also mention, look at the circuit, you have to understand, because physically understanding, and a lot of times you say, well, you talk too much about the physics, you just show us equations, and then what do we do there? You have to understand the physics. Equations is a way, is a language, all right, to understand what is happening in physically speaking. You have to understand the physics. You look at the equations or you look at the circuit and you need to understand what is happening. So here, for example, what I understand is that this is my capacitor. I'm designing, this is a capacitor, all right? This is an MIM capacitor, this one here. And practically my capacitor comes out of this region. In fact, if I wanna remove that, I will do it a little here. My capacitor comes from here, all right? So I need to understand that this is my center piece. So this is my capacitor. Then I look, I'm not gonna design an MIM capacitor and have a horrible capacitor, okay, obviously. So the dimensions that I have given for this one was like the thickness, all right? So the MIM capacitor, if you look at this by itself, is like this. It's like a parallel plate capacitor, practically, okay? And then it has a dielectric in between. So what is important in a parallel plate capacitor, let me just do it here simply from previous classes, is the area here, all right, area, the distance here, thickness, and the material you have in between, epsilon. Do you agree with that? This is important. Why? Because how do we get the expression for a parallel plate capacitor? A parallel plate capacitor is epsilon area divided by H. So this is my centerpiece, C. And nobody has given you that. However, you know, this is what you get out of the center, out practically. That's how you design that piece there. You design that piece there, you design your capacitance, and then you try to find what is going to happen with all of the other parasitics that you see, which are all around it. So practically, this is your centerpiece, and everything else is a parasitic. Okay, where are the other parasitics coming from? Since we talk about only one type of an element, we are going to only talk about capacitors right now. So how many other types of capacitors do I have? Two more. I have one capacitor here and one there. And when do they come from? They come from different types of different parts of the geometry. So C1, according to here, which is there, if you observe that, C1 comes from this dielectric. Practically, why is that? Because I have my lines, which are here. My metal lines are these ones. Okay, you see them? This is my metal here, and then here with an opening. There's an opening there. And then I have metal down here, obviously. So I have capacitance, parasitic capacitances from my metal up here to down there. So I have this one. Let me, in fact, do them. I have this one. That's my C1, is there. And then what else do I have? I have another dielectric, which is the oxide. And then you have seen, for those of you who did MOS, MOS devices, you have an oxide, and then you have, the oxide is that, you have on top of the, or I may make the oxide with a different color, sorry. Okay, that's your oxide. And on top of the oxide, which is here, you have these metals. And then underneath the oxide, you have other metals, because you remember a CMOS has 6 metals. And you're using for your capacitors the top metal, because you want to be away from other metals and reduce the parasitic capacitances. But you have another parasitic capacitance between the top metal, which is this one here, and whatever metal comes underneath your silicon oxide. And these ones are the C oxide. This is the C oxide, which you see here. All right? And then in fact here. So now you found the relationships for your 3 capacitors. You know that in this design, your masterpiece is this one. This one. If your C oxide is, and your, excuse me, did I say that one? Sorry. This one here, that's your centerpiece. This is your main capacitor. You know that if C oxide and this one become large, then we have a problem, because these 2 capacitances here and here, all right, we see them symmetrically, will become big, and they will start impacting the value of your capacitance that you have decided to design. Okay, so, but I have to calculate them. So what I do, I use the formulas, all right? And in fact, I find, first of all, that C1, which is the capacitance that goes all the way down to the metal after the 200 micron thick dielectric of silicon, then this C1 is much smaller than C. Of course, it's much smaller because H is much higher. H is much higher, all right, than D. So we expect our capacitance C, which is our masterpiece, to be much higher than C1. We expect to see that. Anything else if you do, and if you see a C1 to be the same of C, then there is something is hugely wrong there. Okay, then I go and I calculate C oxide, and on the basis of what I found, C oxide is 1.4 femtofarads. And I also want to tell you the following. It says there that it has already incorporated into this data that I gave you from a book, and then it was from a paper. They have already incorporated the units everywhere. So what you really only have to do is to put the values of L and W in micrometers, and D in micrometers, and F in numbers of gigahertz. All right, so they have already taken care of the conversion of units. So as long as you keep all your distances in micrometers, and what else it says, capacitances will come immediately in picofarads, inductances in nanohenries, and your F, it has to be in gigahertz. You don't put hertz for F. If it's 1 gigahertz, you put 1. If it's 2 gigahertz, you put 2. Okay, that's how it goes. Okay, now I have to calculate my C. But C, they have not given me a formula, it's my formula. So for C, I will have to put all of the parameters here, but I make sure that I get C as in picofarads. Here, of course, is a very small number, so practically my C is in femtofarads because this is a small MIM capacitor. Okay, so no, 2.8. What did I do? 2.8.
Dr. Katehi,
Yes.
I think it's already the end of class.
It's already late. Okay, so what I will do here is that I will continue at this point at 3. And I will tell you how to continue after that in your solution. So I will show you how to calculate the individual, how to think when you calculate the individual capacitances. Then we'll go to inductances, and then we're going to go to resistances. And then from that point on, you're going to have to do the rest of the problem. Okay?
And,
so at 3. Yes.
okay. Are you going to post to the video screen, video recording?
No, not at 3. And I have to tell you why. It takes me an enormous amount of time to do the video comes. Most of the video recordings come, for some reason, I don't know what the problem is with Zoom, or it might be with eCampus, because I do through everything through eCampus. My recording, a lot of them are, they are in places I have to do editing. And the editing takes me an enormous amount of time. So I will do the video for the lecture, but for office hours, I will not do the video. I will do only my notes. So I'm telling you that.
You will post the notes?
Yes, of course. The notes are very easy to post.
Oh, okay. Because
what is difficult is the video.
The notes.
The notes, I will post them, of course.
For the homework.
Well, the notes I'm covering now, I'll post them. They're not secret. Whatever I need to show you, I write it. I show it to you. And from the time I show you something is public. Yeah.
Okay. Okay.
I have a question about MIM caps.
Yes.
So for the layout, would it be a valid strategy to reduce the parasitics if I just take out some of the ground plane under the capacitor?
Yes. If you don't need it, you take them out. Absolutely.
Cool.
Yes.
How significant are, like, I know it's a hard question to answer, but like how off, like on average, how significant are the parasitics?
You know, the biggest problem with the parasitics is that they lower your resonant frequency.
Ah,
And so what is resonant frequency? At resonance, your capacitor looks like an inductor. All right, you remember how it's the
Right.
resonance is like, yeah. At resonance is exactly the point where your capacitor changes from capacitance to inductance and the reverse. So you want to be so far away from resonance as far as you could be.
interesting.
And so, for example, in this capacitor, you will see that you can make an easy calculation for the resonance and it will be at 650 gigahertz. That's how far you want to be from it.
Impressive.
Yeah.
And then I was looking at this picture and I had another question.
Yeah.
It seems to me like you would get some kind of fringing capacitance between,
Yes.
yeah. Is that significant or is that?
This paper, it has already been incorporated.
Okay.
If you're, for example, if in this particular case, and let me in fact clean up some things here. In this particular case, if you look, D is 10 microns and W and L are 30. So in this case, I would say I can ignore the edge effect.
Okay.
Because the thickness between the metals is less than 1/3 or 1/3 of the width and the length. So if I were to go and include parasitic effects, there will be minimal compared to what you get from the other problems, like from here. All right. Okay. They will be up here. You will have an additive capacitance. So for example, the field here, if I were to increase it, the field here, let's say, goes like that. All right. Fringing means that it's going to look like this here.
Yeah, that's exactly what I was thinking about.
Yeah, and if you have fringing, that implies that you have an additional capacitance here.
Right.
Then you add it, but it's going to be so small.
Okay.
Then it's not worth it. And
I kind of thought on the right-hand side where it has that right angle, that's just like a second parallel plate capacitor.
Yeah,
at 90
but
degrees.
Look, this is, yeah, I understand. But here, the area, this is probably like 2.
Yeah.
This is like 2.5 microns. That might be probably, who knows, it could be even a little bigger. Depends on how they make it.
Right.
So so practically the capacitance is going to be like this.
Okay. Small area, so not a lot.
Very small.
Yeah.
Yeah.
Okay. Cool.
Yeah.
Okay. So those are all my questions. So.
Okay.
Appreciate it.
Sure.
Dr. Takehi,
yes.
I have a quick question about the project for this
yes.
week's assignment.
Yes.
So when we're looking at the matching networks to match the real part, we were wanting to use a quarter wave transformer, but you have to change the characteristic impedance of the line to do that. Are you allowed to do that within microstrip technology?
Of course. You know how you do that? If you have, for example, it's very easy in microstrip. If your microstrip on top, looking from top, all right? That's the signal line. This is say, for example, a microstrip that is on a low, let's assume that this is silicon oxide, all right, for a moment. Let's assume that this silicon oxide had 5 microns. And then epsilon sub r, in this case, is going to be like, let's assume that it's like 2.6, I will put here. Approximately a 50 ohm lines will be somewhere between 5 and 10 microns. Okay. Let's assume that I want to do a line which is 80. Then I just make it narrow, more narrow on the top like this. So if this is 50, this is going to be 80.
Okay, that makes sense. Thank you.
Yeah, sure.
What is the P, the permittivity value was it left out of the homework, or was there an equation?
Whose permittivity? Oh, mu.
Or not the
permeability.
The resistivity of the metal traces. So,
if you go aluminum, it says aluminum, you can find it. If you say resistivity of aluminum, you can find it anywhere.
It's about 2.65 times 10 to the negative 8 meters per ohm. Meters ohm.
Yeah.
Which this leads to my question.
Yes.
Which you see the delta on the formulas?
Yes.
Yes. In order to make this work, to get that delta into micrometers,
yes.
Do we just leave resistivity in meters per meters ohm, or we put in micrometers ohm?
You make it micrometers, but F, you keep it in numbers. Like F is going to be, if it's 1 gigahertz, you make it 1.
Yeah, I heard that part of the lecture.
Yeah.
I was wondering about resistance.
But the other thing you can do, first of all, it's very interesting. That's the other thing that I like about these kinds of problems. You see the interesting thing in that I will talk about it later, is that this, this one is like a constant, 1 over square root of F. See that?
Yes.
So if you go, you can find the delta, which is the skin depth. This is called the skin depth.
Yes.
Okay, you can find the skin depth for aluminum, and they will give you the value at 1 gigahertz. It's from the maker. And then you take the value of 1 gigahertz, you divide it by square root of F, and that's it.
All right.
Yeah.
All right. Thanks.
See how you can do that?
Wait, so is F, are we supposed to solve for that, or because we're supposed to plot the equivalent impedance in relation to W, right? And
yeah, so you can see here what you're referring to. So it's very interesting on how this F is important. All right, you see? This F, all of the resistors, all of the resistances, and that's something to keep in mind, that come out of metal losses, the resistance, the equivalent resistances that are due to metal losses, they vary as square root of F. But the equivalent resistances that are due to the electric losses, they vary as 1 over F. Excuse me, as F. Did I say 1 over F? I have to correct that. I will talk about this later, as F.
I'm still confused. Are we supposed to leave it as a variable, or are we supposed to?
As a variable.
So in that case, should we convert it to W, radial frequency?
What do you mean? Omega, you mean? It's not W.
Oh.
Yeah, you can convert it into omega, of course.
Because for the next for number 3 on the homework, it's asking you to plot it. And so plot it with omega being the independent.
You can plot, frequency can be, omega can be, with omega being like as a function of frequency, it says, yes.
Mm-hmm.
And I will not plot, you know how to use MATLAB?
Yeah, a little bit.
If you know, do you know how to use any other software to plot things?
I mean, not really, but I'd have to.
I think it will be very useful to learn those things for your own, as an engineer, will be nice to know that, because if you go out to work, you're gonna have to know them. Mm-hmm. As for example, something like that, I may do it on my own. I may try to calculate it. It's so time consuming, and then everybody's using MATLAB nowadays to do these kinds of things. So you leave your square root of F and then you do the plotting easily. In your case, what I would do if you don't do that, then I would just give a few frequencies, because it's not gonna be if the resonant frequency is so high up, it's going to be kind of smooth, the performance of the Z naught. And you can excuse me, get a few points, unless you want to go and plot it around. Did I say around? No, I say calculate and plot it as a function of frequency. So if you wanna, you can just, if you don't have any way of plotting it through a, like a plotting routine, I would say just I would get a few points, and then I will calculate for those points and plot them. But it will be easy to do it on a MATLAB or something else, whatever else you may have. Do they have, a question I have, do they have MATLAB as a requirement?
No. Well, when I first came to A&M in the Introduction to Engineering course, they ran us through MATLAB, but I don't think the university provides it anymore.
They do now, I think.
You do. You go to Software Center and you can get it for free.
In the
Oh, really? They put it back?
Yeah.
Yeah, they got the license back.
Okay.
Oh yeah, they have MATLAB and they have all kinds of things of MATLAB. Because I have to tell you, it's like today's like a calculator. I mean, before MATLAB and all kinds of things, we will all do our own little software, write it and run things. But right now, why doing things, unless you know Python really well and you do it there? I don't know. I mean, I
So for example, you said solving for what's this squiggly thing called again? What's the terminology for it? It looks like a music note.
That's lowercase delta.
Lowercase delta. Yeah, so when you solve for R, you have, is your final result supposed to be a function or is it supposed to be a final value?